Welcome to yet another webinar in our series on the microbiome and your health. My name is Guy Daniels, and I'm the head of medical education for Onegevity. This is essentially part 2 of our topic, metabolic syndrome. Today, we'll review information on non-alcoholic fatty liver disease, from here on referred to as NAFLD, and its possible progression to non-alcoholic steatohepatitis, which we refer to as NASH. Think of NAFLD as diabetes of the liver. Like any condition, it doesn't hit hard all at once, but gets worse with time. NAFLD is essentially stage 1, that of steatosis or lipid accumulation. NAFLD is diagnosed technically when intrahepatic triglyceride content is greater than 5% of liver volume or liver weight, or histologically defined when 5% or more of the hepatocytes contain visible intracellular triglycerides. NASH is stage 2, so to speak, where the term hepatitis is used, which means liver inflammation. The next stage would be cirrhosis, which is when scarring from chronic inflammation occurs. The prevalence of NAFLD is estimated to be 20 to 30% of the general population in Europe and the United States. It doesn't always occur in the obese, as it's diagnosed in 15% of the non-obese patients. But the numbers rise dramatically with the corresponding weight, as 65% of the obese and 85% of the extremely obese are diagnosed with NAFLD. About 15 to 25% of those with NAFLD will develop NASH, which along with the inflammation results in some degree of fibrosis. And of these, approximately 10 to 29% of patients with NASH will develop cirrhosis within 10 years, which is a direction you don't want to go. Now notice both conditions start with the word non-alcoholic. This implies that liver damage was not from 3 or more drinks a day, but from overall metabolic and microbiome factors. However, don't let this term fool you, as you will soon see you can ferment very appreciable amounts of alcohol in your microbiome, regardless of alcohol consumption, which can play a significant role in NAFLD progression. So what does this look like from a labs and microbiome viewpoint? Well, on this slide, we have the lab work listed, and no surprise, the usual suspects are on there. In regards to anthropometrics, the NAFLD subjects were not obese. As we said before, about 15% of non-obese subjects have NAFLD, but this varies. For example, in East Asia, it's closer to 20%. In India, it's much higher. What counts more here is where the fat is located, as central adiposity is not a good thing. When we look at the microbiome, these authors noted that the NAFLD subjects had significantly higher gram-negative and significantly less gram-positive bacteria. Now, this is a very rough guideline. Generally speaking, your gram-negative bacteria can cause inflammation much more so than gram-positive. But this isn't always the case, as one of our superstars, Akkermansia muciniphila, is gram-negative. But as a general rule, yes, you like to be in the camp with the healthy controls here and have more positive and less negative. So this implies that NAFLD is in part related to inflammation from the gut. Here we see a study in regards to intestinal permeability and NAFLD as it relates to the microbiome. The authors state that the often pathogenic genus Streptococcus displayed a significant 3-fold increase in the NAFLD group. As you can see from the figures, the healthy controls had far better results when it came down to intestinal permeability. So again, we have this common theme through our webinars of bad bugs doing bad things. Here, the bad bugs were from the genus Streptococcus, and the bad things were increasing gut permeability, which in the context of NAFLD puts a great burden on the liver, as we'll soon discuss. In slide 1, we mentioned how your microbiome can ferment sugars into ethanol or alcohol. Here's an example of the variability in gut ethanol production, and this is in children, mind you. When they compared the microbiome of NASH, obese, and healthy children, they found that among those taxa with greater than 1% representation in any of the disease groups, Proteobacteria, Enterobacteriaceae, and Escherichia were the only phylum, family, and genus types exhibiting significant differences between obese and NASH microbiomes. Similar blood ethanol concentrations were observed between healthy subjects and obese non-NASH patients. but NASH patients exhibited significantly elevated blood ethanol levels. You can see from all of this from the figures on the slide. If you recall from our series, these same bad actors come up all the time. Escherichia are your classic opportunistic pathogens, which is but one genus in the nefarious family Enterobacteriaceae, which of all the families in your gut, this is the last one you want to have high levels of. And this family is a subclassification of proteobacteria, which is an entire phylum loaded full of troublemakers. And Escherichia, like many other taxa, produce ethanol from their metabolism. Notice that ethanol is never zero for any group, including the healthy controls. Many taxa, including good players like Bifidobacterium, can produce ethanol as a byproduct of their metabolism. You just don't want excess. Alcohol leads to increased intestinal permeability in the gut and oxidative stress, in this case in the liver. Also, the extra fat deposition from NAFLD sensitizes the liver to alcohol insult. So even a relatively lower level of alcohol is sufficient to cause inflammation and potentially fibrosis. And of note, reported ethanol levels in NAFLD can be above the legal limit for driving in the United States. Here, we also have a slide looking at NAFLD in children and their microbiome as it relates to ethanol production. Again, we see in the NAFLD group, they had more than twice the serum ethanol. And as you can see, ethanol metabolism requires this molecule called NAD. NAD is a complex story, but think about it as potentially the most crucial player in this whole system in both ATP production and sirtuin-driven metabolic benefits. And as we'll see later, both ATP and NAD levels are not ideal in NAFLD. And whether you consume alcohol or produce too much from dysbiosis, you're also further depleting your NAD stores. Once again, we see increased alcohol here in adults with NASH. Again, we show on the bottom left our alcohol metabolism. The first enzyme requiring NAD is alcohol dehydrogenase. The second is aldehyde dehydrogenase. In these subjects, the increase in alcohol was measured by the upregulation of the genes for these enzymes in order to produce more enzyme activity in order to process more and more alcohol. Not only were these genes increased in NASH, some dramatically so, like the 40-fold increase for ADH4. Additionally, genes related to liver inflammation and fibrosis were also found to be elevated in NASH livers compared to normal livers. This microbiome alcohol connection is known. A condition entitled autobrewery syndrome, as the name implies, produces excessive amounts of alcohol within the gut. My slides and points are not about autobrewery system, as it is the rare result of one particular species or strain having grown out of control for whatever reason, like the individual here in this slide, with high levels of a species from Klebsiella. I am talking about the overall alcohol producing capacity of the entire microbiome. But back to this slide to illustrate a point. These Chinese researchers decided to go looking for this high alcohol producing strain in subjects with NAFLD, NASH, and healthy controls. They found that 61% of NAFLD patients carried the high and medium alcohol producing strains, while this value was only 6.25% for healthy controls. When they transplanted the whole microbiome into mice, they too developed NAFLD. When they transplanted the whole microbiome minus the problematic strain into mice, the mice did not develop NAFLD. I hope these slides illustrate the importance of dysbiosis and alcohol on liver function. And by the way, Klebsiella is not just an alcohol producer, it's a bit of an opportunistic pathogen in the same bad family as E. coli, and something we'd want to identify and minimize in your protocol. So let's leave the topic of alcohol and dive into the liver. In order to appreciate the biochemistry of what's going on from a metabolic viewpoint, think of yourself as a bear trying to get ready for hibernation. You need to stimulate a number of pathways in your body to store fat. In order to do that, you eat as much as you can, and your biochemistry does the rest. This same is true for humans. But in NAFLD, there is an accumulation of fats, which in excess cause inflammation and possibly damage. These hepatic lipids may be derived from diet, from excess fat tissue or something called hepatic de novo lipogenesis, DNL for short. The simple translation for hepatic DNL is that the liver is making fat from scratch. DNL is a process by which lipids are synthesized from dietary sources, usually carbohydrates. Remember this for our upcoming slides on fructose, and also from other sources. Hepatic DNL is increased in individuals with NAFLD. There are an enormous number of feedback mechanisms in our biochemistry that perpetuate a set of signals. In our case of the bear, we want them to store energy for the winter. And that's what we're doing in obesity. NAFLD, and even more so NASH, is the unhealthy propagation of those signals. For our second mental exercise we have for this slide, imagine your gut is a tube exposed to the outside world and all that it offers. It's a bit like your skin, protecting you from everything you can encounter in the course of a day, week, month, and year. Now imagine all that you ingest, all 60 tons in the course of your lifetime, every aspect of the food to include potential pathogens. All that food continues through the tube in your body, and it's the tube's job to break down those large molecules down to the smallest components so you can absorb them through an enormous network of cells with a surface area of almost 2 tennis courts, but not more than 1 cell deep. Now imagine if intruders got through those walls of this castle into your systemic self. What would be required? Vigilant guards to fend off the intruders. And that's what we have. We have a robust immune system lining our gut and in our liver. When you consider some of the full-time inhabitants of our gut are always up to no good and looking for an opportunity to run wild, you get an appreciation of the challenge. And what if an intruder gets in? It's a battle, which is the immune's inflammatory response. So now consider that the liver received most of its blood and nutritional supply directly from the gut through the portal vein, and it's the first organ to be exposed to gut-derived toxic factors, including whole bacteria or bacterial byproducts such as lipopolysaccharides, LPS, which we commonly refer to, among others. LPS is recognized by the cell receptor TLR4, which is not only present in almost every cell in your body, but is also activated by saturated fats, interestingly enough, further linking diet and pathogens to liver dysfunction. The liver's central player in its defense is its version of a macrophage called a Kupffer cell. Kupffer cells are located at the crossroads of the portal vein and hepatic artery tributaries. They recognize, ingest, and degrade cellular debris, foreign material, or pathogens, and exert a central function in orchestrating inflammatory processes. They are so important that approximately 15% of liver cells are Kupffer cells and are the largest tissue-specific population of macrophages in the body. But when stimulated by these bacterial signals, they set off an inflammatory response, as one would hope for in the presence of an invasion. And at low and finite levels, this is fine, but at high levels in the chronic state, this continual inflammation has an enormous cost. As a result, this chronic activation of inflammatory macrophages and stellate cells promotes the progression from steatosis to NASH. This ramped up inflammation unfortunately ties back to the metabolic state in a vicious circle, as TNF-alpha, a key member you now know from the inflammation cascade, has been shown to impair insulin signaling, increases ROS synthesis, and induces a key protein, SHRB1C, which you can think of as the hibernation instigator, worsening metabolic dysfunction in the liver. So if you order up a kit with us, and in the questionnaire you note that you have prediabetes, type 2 diabetes, NAFLD or NASH, then among the dietary recommendations, one will certainly be to reduce your intake of fructose overall, but in particular foods such as sodas, which contain very high levels of high fructose corn syrup. As dietary recommendations are a part of our platform, I'd just like to address this one at length within this webinar. Why? Because I want you to understand the whys and wherefores of this recommendation, and hopefully you'll seriously consider the following this part of your program if this information sinks in. Let's start with some background information. Fructose has the highest relative sweetness over all sugars. Therefore, it is exploited in soft drinks and other commercial products. If you consider that honey, dates, raisins, molasses, figs, grapes, raw apples, apple juice, persimmons, and blueberries have a content of only 5 to 10% of this sugar, then the 50% fructose in table sugar might sound high. However, the most common form of high fructose corn syrup has 55% fructose, and certain popular sodas and other beverages contain a fructose content approaching 65% of sugars. Moreover, high fructose corn syrup can be made to have any proportion of fructose as high as 90%. Fructose consumption has increased 300% in the past 20 years. Added sugars account for 15% of overall energy intake in the Western diet, and are even higher among adolescents. US adolescents ingest an average of 94 grams of added sugar per day. Because a high-fat diet has long been recognized as a risk factor for the development of NAFLD, the public has heeded this warning, and total intake of fat has stabilized in the last 30 years, and the percentage of calories ingested from saturated fat has decreased. However, what is not so well publicly known is that a high carbohydrate diet of equal calories supports DNL, more than an equivalent diet containing less carbohydrates and more fat. And within these carbohydrates, high fructose corn syrup is the worst culprit. In NAFLD patients, increased daily fructose ingestion is strongly associated with low HDL, the good cholesterol, hyperuricemia, which we'll get to soon, high triglycerides, increased fibrosis severity, and increased hepatic inflammation and hepatocyte ballooning, while fructose restriction leads to improvement in NAFLD. Additional studies have found that fructose consumption is increased nearly 2 to 3-fold in adults with biopsy-proven NAFLD. So what's going on with sugars, and in particular high fructose corn syrup? Well, because of the differences in how fats and carbohydrates are absorbed, the liver is immediately exposed to a much higher level of sugars than the rest of the body. And this is more true for fructose, as fructose is almost entirely cleared by the liver. Although both glucose and fructose are metabolized through the glycolytic pathway, the rate-limiting enzyme is bypassed in fructose, which floods the liver with fructose 1-phosphate. This results in a drastic depletion in ATP, the basic unit of energy. The liver is unable to recycle spent ATP, and as a consequence of a variety of signals and proteins, too much of the ever so valuable ATP gets completely spent in the form of uric acid, hence our connection to hyperuricemia. This is shown in studies where reduced hepatic ATP stores are shown to be more prevalent in overweight and obese subjects than in lean subjects. And the measurement of uric acid is a sensitive index of compromised cell ATP homeostasis. The ATP depletion has big consequences in oxidative stress and intracellular protein production in particular. Then there's the fructose itself, which, as a powerful intracellular signaling molecule, activates a multitude of major regulatory proteins, which play big roles in all things leading to metabolic syndrome. And the feedback mechanisms ensure a spiral downwards. For example, continuous exposure to fructose results in the upregulation of both its absorption and enzymes involved in its metabolism, in insulin resistance, and a variety of other feedback mechanisms which ensure metabolic dysfunction. Two of these are gluconeogenesis and lipogenesis, both of which consume even more ATP. So now you can begin to see how someone in the overfed state, who doesn't suffer from a caloric deficiency, but does suffer from a lack of energy in their daily lives. To confirm a small portion of the biochemistry of what we're discussing here, researchers examined the relationships between dietary fructose, uric acid, and hepatic ATP depletion at baseline and following intravenous fructose challenge in low and high fructose consumers. As one might expect, the high fructose consumers had slightly lower baseline hepatic ATP levels and a significantly greater absolute drop in liver ATP following the intravenous fructose challenge, as you can see here to the right. So what's going on here is that when someone's liver energetic capacity is already challenged by high fructose consumption, the introduction of a fructose load even more compromises the biochemistry of the liver versus others. Similarly, a study of diabetic subjects revealed that high dietary fructose intake leads to lower hepatic ATP levels as long as 50 minutes after a fructose load. None of this is good when you consider that the liver has very high energy demands, as its metabolic rate is similar to that of the brain and is nearly 20 times greater than the metabolic rate of resting skeletal muscle. And although the liver weighs only about 2.5% of total body weight in the lean, it accounts for about 20% of total resting energy expenditure. There are a few key supplements which have excellent data in the support of NAFLD and NASH. For example, various curcumin products and trials have shown some remarkable results. Another key consideration would be milk thistle, but these are really outside the scope of this presentation. Here we highlight the microbiome and its impact systemically. This is not to say that various herbs won't alter the microbiome, they do, but the mechanisms behind them lie largely via different pathways. However, there is one phytochemical supplement I do want to highlight, resveratrol. I bring this to your attention not only because its administration in trials has been overall quite successful, but it reinforces a key concept within this presentation, that of ATP availability, which brings us to a caution on the use of high-dose long-term resveratrol. But first, let's take a look at this slide. In this Chinese study, subjects received either placebo or 600 milligrams per day of resveratrol for 3 months. I will tell you that's a pretty high dose. A dose which should drive changes, and it did. It significantly reduced liver enzymes, glucose, HOMA-IR, which is a measure of insulin resistance, total cholesterol, and LDL cholesterol. So how does resveratrol make these beneficial changes happen? Well, that's another webinar which you can find on my LinkedIn account, but simply put, it increases the binding affinity of 2 key sirtuin enzymes, which drive many beneficial changes via other proteins, based on the recognition of calorie restriction, which is as old as life itself, going all the way down to yeast and bacteria. The problem in doing this at high doses for long periods of time is that it can deplete NAD stores. NAD is integral in the sirtuin process, but it also has other very key roles in the cell. One of these roles is in the generation of our previous friend, ATP, the basic unit of energy for life. Hopefully, after having gone over ATP in our fructose slides, you can begin to gather an appreciation for it, and it's something we certainly don't want to reduce. So if you or your doctor do decide to use resveratrol to support your liver health, I'd recommend taking a compound called nicotinamide riboside with it, which will support NAD levels. Now let's take a look at measures which are within the scope of this presentation and are more in line with tackling NAFLD and NASH from the perspective of the microbiome. This slide is interesting for a couple of reasons. For starters, we're dealing not with NAFLD, but its more serious progression, NASH. Here, 66 courageous subjects submitted liver biopsies to determine the level of NASH. This study is also a bit more akin to what we're doing at Onegevity, in that these researchers administered Bifidobacterium longum, a probiotic of essentially universal benefit, and FOS, which is a prebiotic, for 24 weeks. These are the types of things that we recommend based upon your questionnaire and lab results, but our recommendations are more varied and at higher doses unique to your needs. So what do these researchers find? Well, at these low doses on this slide, you see significant improvements in key markers for systemic inflammation, insulin sensitivity, serum LPS, reduced serum and liver lipids, and a significant decrease in liver inflammation. If there were a drug that could do all of this, it'd be a blockbuster. But as we've learned, there is no approved drug for the treatment of NAFLD and NASH. What we're doing here is addressing this condition right at the root cause, which is what we do in functional medicine. In this study, 50 biopsy-proven NASH patients were administered a regimen as described on the left side of the slide. The probiotic count was extremely low, and to be honest, based upon our meta-analysis, I would not have chosen this species anyhow. The 2 prebiotics that were used, inulin and partially hydrolyzed guar gum, are both outstanding prebiotics with a great deal of data, particularly inulin. However, here the dose administered was a little low, only at 8 grams per day. Although a number of measured parameters did not significantly improve, there were important ones which did. As you can see from figure 1, the amount of steatosis, which is liver fat deposition, was reduced significantly in the symbiotic group versus controlled as measured by MRI. There was also a significant drop in weight, which is something desirable for most everyone from an aesthetic and health viewpoint. Lastly, serum uric acid levels were decreased, which, if we recall back to our fructose slides, indicates improved energy dynamics within the liver. So isn't that interesting? The ingestion of prebiotics resulted in increased liver ATP and less weight and liver fat. I know it's hard to fathom, but I try to explain these complex relationships as we go through these webinars. Similarly, in this study, the researchers also used a symbiotic, which is prebiotics plus probiotics, in 52 patients with NAFLD. They were supplemented twice daily for 28 weeks with either a symbiotic or a placebo. Both groups were advised to follow an energy-balanced diet and physical activity recommendations. Like our previous slide, the doses of prebiotics used were far below our recommendations and not specific to each subject's microbiome. Even with that said, the results were quite impressive. All 3 scores for liver function tests were significantly reduced. Although this is rightfully considered a good thing, these scores are not the end-all be-all of measuring liver health, as it is important to highlight that liver enzymes cannot be considered a reliable method for diagnosis and follow-up, with several studies confirming all ranges of hepatic fibrosis in the presence of normal liver enzymes, and are usually normal or minimally increased in NAFLD. But one thing that is a great measure, and remarkably was reversed, was liver fibrosis, the scarring that occurs from chronic inflammation in the liver. The other impressive findings were that the 3 classic markers of inflammation, high sensitivity CRP, TNF-alpha, and NF-kappa beta, were all significantly reduced in the symbiotic arm versus the placebo group. Again, we're addressing the root cause, the underlying biochemistry of a series of events, which results in inflammation, scarring, cell death, and possibly organ failure. Now, if we take this condition a step further, we see manifestations in the brain. Here we're dealing with minimal hepatic encephalopathy, MHE, which is highly prevalent, 22 to 74%, among patients with liver dysfunction. As the name implies, there is a liver-brain connection. So what's going on with these patients? In short, due to their compromised liver function, they are not able to clear and eliminate ammonia well. Its accumulation in the brain ultimately leads to certain brain cells swelling via osmosis. This neurological phenomenon leads to impairments in attention, visual spatial perception, speed of information processing, especially in the psychomotor area, fine motor skills, and short-term memory. This in turn leads to significant increases in undesirable events, such as more car accidents and falls. You can see from Table 1 that MHE can get much worse with a deterioration in liver function. When the researchers took a look at the fecal microbiome, they saw, as they put it, substantial derangements in the gut microecology, with significant fecal overgrowth of potentially pathogenic Escherichia coli and staphylococcal species. These opportunistic pathogens should be familiar names to you by now, if you've been following this webinar series. Escherichia coli, or otherwise known as E. coli, is the classic bad actor in the gut. And many species within the genus Staphylococcus are also nefarious opportunistic pathogens. So to see an abundance of these 2 in cirrhosis is not a surprise. The researchers administered either a symbiotic preparation, Group A, fermentable fiber alone, Group B, or a placebo, Group C, for only 30 days. Here, the prebiotic blend was in a bit more accordance with something we'd recommend from a couple points of view. So what did they find? As you can see from Table 5, there was a significant drop in serum ammonia in both groups A and B, but not in the placebo group C. So there were improvements in overall liver function, which allowed more clearance of ammonia from the blood, which as an end result should improve brain edema. Another finding was a significant improvement in serum endotoxin. That's a synonym for the LPS we keep mentioning, which we know by now, its recognition by TLRL4 often results in drastic increases in inflammation. And as we recall from our previous webinar, not all LPS is created equal, as the LPS from E. coli can have 100 to 1,000 times the inflammatory potential as LPS from other not so nefarious gram-negative taxa. When they looked at the microbiome at the end of the study period, they found that the symbiotic preparation led to significant reductions in the viable counts of both the opportunistic pathogens, with counts falling to levels comparable to those in healthy controls. For the prebiotic-only group, there were significant reductions in counts of both E. coli and the genus Fusobacterium, another set of potentially bad actors, and overgrowth of E. coli was reversed. Also, the genus Bifidobacterium became the predominant marker organism in feces. All of this from 30 days on a reasonably well thought out program that wasn't even specific to the individual. I hope these last 3 slides give you a feel for the power of what can be done with the appropriate strategy. The goal here is to supply the good bacteria with the fuels they need to survive and thrive. They in turn change the environment of the gut via various mechanisms, which results in fewer bad actors who previously enjoyed a different gut environment. This in turn results in better overall function of the many cells which line our gut, which improves an enormous array of factors, one of which is gut permeability. This then results in fewer foreign proteins and peptides making their way into the rest of the body, which then results in a decline in immune stimulation, which reduces inflammation. Inflammation is key in a wide variety of symptoms and diseases, some of which we've covered in this series. I realize that the combination of the microbiome, cellular biochemistry, and our immune system are impossibly complex, but it boils down to a relatively simple equation. If you've been lucky to have been a vaginal delivery, exclusively breastfed for at least some months, been exposed to minimal rounds of antibiotics, have eaten a healthy diet, enjoy a relatively stress-free lifestyle, and didn't inherit any bad genes, then odds are you're great. But if you're not this fortunate, which very few of us are, then we need to drive serious changes starting with your gut. Exercise and a proper diet can go a very long way when it comes to metabolic syndrome. It's the first line therapy for NAFLD. But how many can comply with that? As the numbers show us, more than 50% fail to achieve the target weight loss. The numbers aren't good. So let's drive the needed changes using precise recommendations in a regimen which can have high compliance. Our next webinar will be on how the microbiome impacts the development of autoimmune diseases. Until then, tell your loved ones about this information, have them visit our website at onegevity.com and order up a kit. I've been able to turn around many dysfunctional guts over the years, and maybe we can help you or your loved one out as well.